Okay, welcome everyone again. Today we have speaker Professor Ilaria Pascucci. Ilaria has a master's degree in University of Bologna and then a PhD in University of Heidelberg. And her advisor was Thomas Henning. And she did thesis on massive star formation at high spatial resolution. Massive stars. I was very fascinated about it. I'll talk to you about that later. And then she joined here as a postdoc, and that's where actually I met Ilaria as a postdoc for PEPS. It was a formation and evolution of planetary systems, Spitzer legacy team. And then after that, she joined Johns Hopkins University, and then she was a staff member in Space Telescope, and then we were successfully brought her back to the University of Arizona, and she's a professor here. And she works on, as you know, planet formation, circumstellar disk evolution, and exoplanet population studies. And she's been on a lot of awards, including the Blitz Award last year. And she's a team lead for the Alien Earth program. And then she was also a part of the leader of Earth in Other Solar System, our astrobiology program. So Ilaria, take it away.
Yeah, thank you very much, Serena, for the introduction. And thank you all for being here. Those online, can you hear me well? Hopefully so. All right. Yes, okay, perfect. Okay, so my goal today is to summarize some of the recent results, findings that we have from the Atacama Large Millimeter Array and the JWST regarding disk evolution. But I also want to place these results, these new results, in context of previous work, a decade of work that we have done here at the University of Arizona in my group, so that you can better appreciate the new findings. So this work was carried out with many collaborators. The main ones are listed here. And the names of current students working with me at the LPL are highlighted here in boldface, and I will mention also some of their work in this presentation. All right, I cannot advance. Now I can, okay. All right, so we start from this schematic picture, and of course I'm not going to explain to you because you all know these different stages of disk formation and planet formation. But what I want to highlight here is that the focus of this talk will be on the gas content. And we know that initially protoplanetary disks are very rich in gas. The dust is only about 1% of the total mass. But by the end of this evolution, after planets have formed, most of that gas is gone. You can think about our solar system, and so the masses, for instance, of Jupiter and Saturn, the gaseous planets in our solar system, contain less than 1/10 of the minimum mass solar nebula. So again, there most of the gas is gone. And even if you look at exoplanetary system, we know that gaseous planets are actually not that common. Just about 1 out of 4 stars have a giant planet. So what happens to the gas? Part of it, it's accreted onto the star. And we will see today that there is not only accretion, there are other ways to disperse that gas. So we know from many indirect observations that from the early stages to the latest stages, young stars that have a disk accrete that disk gas. But accretion also poses a major challenge to understand how disks evolve, because as written here, the specific angular momentum of the gas increases with radial distance. And if you want gas to accrete onto the star, some angular momentum has to be shed. So the key question here to understand the disk evolution is actually which mechanism lead to angular momentum loss. So today I will be focusing on the 2 main contenders for redistribution and removal of angular momentum. The first one is a so-called turbulence-driven accretion. This is, if you want, the more classic view of how disks evolve and disperse. So as illustrated here by these orange arrows, the main idea is that the disk is turbulent and somehow angular momentum is redistributed outward, and that enables part of the disk material to accrete onto the star. To disperse the disk in this classic scenario, high energy photons from the central star are important. So the main idea is that they heat and ionize the disk surface, and that surface becomes hot enough that leaves the system in a what often called a photoevaporative or thermal, relatively slow wind. But more recently, detailed simulations of disk evolution have shown that likely disks are not that turbulent. And so they have proposed a different paradigm for accretion. This is the one in which magneto-hydrodynamic disk winds remove angular momentum from the surface of the disk. They remove matter and they remove also angular momentum. So here what happens, imagine that you have some residual magnetic field from the star-forming region. That magnetic field is threading the disk, and if the magnetic field lines are sufficiently inclined, they can essentially remove the material from the disk away and thus remove angular momentum. Typically, an analogy that is made here is the one of a bead on a wire. So if you essentially rotate that wire, the bead, if there is no friction, is going to just leave the wire moving outward because of the centrifugal force. So this is not a perfect analogy, but it's something that you can think about in your mind to connect to this different paradigm of disk evolution. So here we still don't know how disks are dispersed. It could be that you have the same type of photoevaporative winds that I mentioned for the classic scenario, or some other theories suggest that maybe these MHD winds do the whole job. They lead to disk evolution and then to the final dispersal as well of the gas. So one of the central questions I think to answer is the following one. What is the dominant mechanism driving disk evolution? And we will see at the end of the talk that this is important for prior formation. So that's why I think this is an important question to answer. And here we can have two different approaches. We can look at population level surveys that trace key star and disk properties. For instance, you can imagine the rate of accretion from the disk onto the star. That's an important property. And then you can test theoretical models this way. Or you can identify outflowing material from the surface of the disk and then try to characterize them. Are these truly the MHD disk winds radially extended that could drive accretion? Because if this new emerging paradigm is the right answer, then of course every accreting star should have an MHD wind driving accretion. So in my group, we have explored both approaches. And so first I will start with approach 1 and then move into approach 2. So we started to look into this very early on with ALMA. This was the beginning of ALMA, so we didn't have the full array, but still we did a survey of an entire star-forming region, the Chameleon-1 star-forming region. And it was a relatively shallow survey, but it provided flux measurements for all the objects that had an infrared axis and therefore the presence of a disk in this region. So then from the measurement of the millimeter fluxes, we could derive to first order the dust disk masses. And this is a plot from the survey paper showing how they relate to the stellar masses. Yeah, I should say that in addition to ALMA, we also did a parallel survey with a very large telescope using X shooters so that we could really characterize properly each of the stars that we observe with ALMA and also measure the mass accretion rate onto the star. All right, so while we were gathering this data, we had several interesting results, but for today's talk, I want to focus on what came out of these two papers, where essentially we used the dust disk masses, we used the knowledge on the stellar masses and the mass accretion rate to test the classic scenario of viscous accretion. I also want to mention, in connection to what happened after this survey, that again, this was a relatively shallow survey, so it took about 2.5 hours to do 100 disks and measure their fluxes. All right, so these are not the data. These are simulated initial conditions. So imagine that you have, as a product of star formation, a distribution in dust disk masses as a function of stellar mass and the distribution of mass accretion rate as a function of stellar mass. As initial condition, we still give a relationship between these two because we know that, as I've shown you before, that these quantities are correlating. So now let's imagine that for each of these points, we evolve the disk through the classic scenario. So a viscous disk, and I should say these are relatively simple models. So we have the classic alpha type disk with a constant alpha, and then we let these disks evolve. So if you look at the population that has viscously evolved, and then you compare the mass accretion rate onto the star with the dust disk mass, you see that even if you start with the broad spreading properties, you should find a relatively tight correlation between these two quantities. Okay, so this is not something new. This is a basic prediction of viscous disk model, and it was pointed out early on by, for instance, Hartmann and collaborators. I should also say that really to test these models, really you need to follow the gas mass, but early on we had only the dust. So what we did was to essentially scale the dust masses, multiply the, scale the gas disk masses by divided by a factor of 100 so that we could compare with the dust disk masses that we have. So this is obviously the gas to mass ratio of the ISM. So it's a big assumption, but let's see what we find. All right, again here model prediction, mass accretion rate versus dust disk mass, and here are the observations. So you can see, yeah, that they look very different. And so we discussed in the paper why this might be the case. We mentioned two possibilities. One I already hinted before, so the first one is that perhaps these disks have not viscously evolved to achieve this tight correlation between the two. But if you look at the ages of the star-forming region, these are about 2 to 3 million-year-old regions. And we know that by that time, 50% of the stars have already dispersed their disk. So it seems unlikely that the disks have not viscously evolved if 50% of the stars don't have their disks anymore. So we discussed this possibility, but we thought it is less likely. The second possibility is the one that I hinted already, is that, well, we only have measurements of the dust disk masses. And what if dust disk masses are not actually a good proxy for the gas disk mass, which is the total mass, closer to the total mass in the disk? So this we felt was an important shortcoming and something that needed to be addressed. And this is one of the reasons, not the only one, but one of the reasons for this large program, this AGE-PRO ALMA Large Program. So now you can see that to measure the gas disk properties, so to detect CO, rare isotopologues, as well as N2H+ that are used to infer gas disk masses, we needed to go much deeper in sensitivity and therefore spend much more time on ALMA. So again, early survey, 2.5 hours for 100 objects, and now we needed 100 hours for 30 objects. So this ALMA AGE-PRO is structured in a way to probe the evolution of the gas disk properties. So we have a young region of fucus, intermediate age region, lupus, and an older region, which is upper scope. There are 10 disks per region with a relatively narrow range in stellar masses, because we know that disk properties scale with stellar mass. And then again, the main tracer, yes, there is a continuum band, but the main tracer, what we really wanted to reach was detection of CO isotopologues and N2H+. As you can see here, this is a large collaboration, so I want to illustrate all the names here. It's important, early career scientists really did an amazing job in reducing and analyzing the data and in writing the amazing paper that came out. Among this group, I also want to highlight the work of Dinshan here, who is one of the organizers of this Origin seminar and also graduate student in my group. If you look at this paper, you will find these beautiful images of the continuum emission and all the CO isotopologues that we traced towards the lupus star-forming region. I also want to mention that all the products from this survey are actually available for you on this website. So if you are interested to use this data set, please do so. The first AGE-PRO results are out. They are summarized in 12 papers. We have an overview paper, and then we have what I call really the foundational papers. These are the papers that describe the data reduction of simple and analysis of the 3 different star-forming regions, and really provide the data set that is necessary for the other papers. For instance, to measure the gas and dust properties, to test theoretical models, and so on. And also we have 2 essentially interesting discoveries, something that we didn't expect coming out from this survey. If you want a figure to summarize the main properties that we find in these disks, I think this is a very good one. It's from the overview paper. And here you can see the estimates that we have of the dust disk masses, gas disk masses, ratio of them, sizes for each object in this different star-forming region. And again, you can look at this as a function of age. This is the young, intermediate age, and older region. So there are many results here, but this survey is not the topic of the talk, so I'm just going to mention this one, that the gas and dust appear to evolve on a different time scale, and in particular, the growth and drift of dust seem to proceed faster than the gas evolution. So in other words, the gas seems to stay longer. Again, there are many results. If you want to, a good place to start is a press release, so you catch the main point. And then, of course, I want to encourage all of you to read some of these papers that are now out. For the purpose of this talk, I'm going to present only one figure from this paper, because it's the one that is most related to today's topic. So Benoit Tabon used the viscous model, so the classic model of disk evolution, as well as new prescription for MHD wind models, and it tested against the observations that we have. So now here, this is, if you want, a similar figure to the one that I showed you early, where you have here the mass accretion rate onto the star as a function now of the disk mass. So this is the gas disk mass, is the total amount in the disk. The data are in red, and the population of synthetic disks from a wind-driven accretion and from a turbulence disk are these small black dots. So from this figure, you can see visually that the wind-driven model does a better job in reproducing the data than the turbulence-driven model. And if you think about the tight correlation that I've shown you before, here you can see the same thing. So the model prediction for the ages of this region is that these two quantities should be more tightly correlated than in the case on the wind-driven model. So this is essentially one of the main results from this paper. I want to note that there is not only this comparison in the paper, so there is comparison also with the sizes. That is also an important comparison, but essentially this is the main result. We should keep in mind, again, that these viscous models are relatively simple, so the alpha is kept constant, and we should also keep in mind that there is a major unknown for the MHD wind-driven model, and that is the magnetic field and how it evolves with time. So that's exactly why I think it's critical to use also the second approach if we really want to understand wind-driven accretion. Do we have winds every time that a star is accreted? Are these winds MHD in nature? Are they radially extended? So again, before JWST, we did a lot of work in my group to identify winds. And so we used high-resolution spectroscopy from the ground to identify them kinematically. So we used different telescopes, Keck, VLT, and of course also telescopes that we have access to here at the University of Arizona, like the Magellan with its MIC high-resolution spectrogram. So what you see here are just a few examples of this large survey over hundreds of objects that we did, just to illustrate the type of profiles, line profiles that we observe. So these are particular lines at optical wavelengths, and thanks to the high spectral resolution, so here we have a resolution of about 5 kilometers per second, we can distinguish different emission components. So we have colored here in green flows that are fast. So 0 is essentially the stellar velocity. So anything that is blue shifted is going away from the star and coming towards us. So again, green is fast outflow, and we know that this is connected to collimated jets. But the other major results from this large survey was the presence of these slower flows that are highlighted here in red and blue. So velocities less than 14 kilometers per second. That seems to be ubiquitous, okay? So we interpreted them as disquint, but note that at this time we were not saying that all winds that we observe are MHD, okay? So at this point, they were disquint. Some components were more likely to be MHD, but at the moment, these are all disquint. Then the other thing we did was a large program, this time at infrared wavelengths, to follow up this other tracer, ionized emission at 12.8 microns. So we knew from previous observations that we did with Spitzer that this is tracing the hot surface of the disk, probably ionized by X-ray photons, stellar X-ray photons. And then from a few follow-up observations that we did from the ground, we saw shifts in this line. So it was timely to do a large program with a VLT. And then in this paper, we essentially put together a sample that had both oxygen 1 data and high-resolution neon 2 data to see what we found together. And this is one of the main findings, and we find that as the mass accretion rate onto the star starts to decline and the inner disk is somewhat depleted, then the oxygen 1 becomes weaker, why the neon-2 becomes stronger. All right, I should also say that all the pre-JWST work is actually summarized in a Protostars and Planet review chapter that I led a few years ago. And obviously the chapter doesn't summarize only the work from our group, but also the work that was done by the entire community. And focuses on class 2 sources, but also traces the class 0 and the class 1 sources. So it's quite comprehensive in that regard. So here is essentially the sketch that we put together when we combined the high-resolution ground-based data at optical wavelengths and infrared wavelengths. So what we thought was happening based on these, the kinematics, just the kinematics, is that early on, when stars are highly accreting, neon-2 is mostly tracing a fast jet. We felt, because we didn't detect a slow component of the neon-2, that there has to be an inner MHD wind that is essentially massive and most likely molecular to essentially absorb those hard X-ray photons that are needed to ionize neon, and therefore do not reach the outer disk to start a stronger outer flow. But then for the lower accrete, or for the more evolved sources, we suggested that that inner molecular MHD wind is essentially reduced, is more tenuous, and only at that time the hard X-rays photons can penetrate the wind and they can launch this slower neon-2 wind that we detected. So there are a couple of main implications here. The first one is that we proposed that there is an evolution in this inner MHD wind, going from more massive and molecular early on to more tenuous and atomic at later stages. And then the other main implication is that, well, if your hard X-rays cannot reach much of the disk surface, then there is not going to be much thermal wind, much photoevaporation at early times. All right, so this was 2020, and so it was also the time to start thinking about JWST. And so in cycle 1, I led 2 successful proposals. One to target these likely higher accreting stars where we expected these molecular winds, and then another one targeting a few of the more evolved disks. What we did was to really focus on the IFU capabilities of NIRSpec, of JWST. So this is for the NIRSpec, is just an illustration to point out that with these capabilities, in each pixel, you can extract a spectrum. And then you can generate images in different components. For instance, we were interested in H2, so molecular hydrogen. Okay, this is not from our data, but it's an illustration. But you can do this type of images that are for specific emission lines. The spectral resolution is not great, is 2000, so it's about 80 kilometers per second, so much worse than what we had from the ground. But really, the novelty here is the sensitivity combined with the small pixel, 0.1 arcsecond for NIRSpec and 0.2 for milli. And you will see that 0.1 arcsecond for NIRSpec is really critical. All right, so first let's start from the more evolved disks. So here we targeted 2 objects that have large dust millimeter cavities indicating some evolution in the inner disk. And at the same time, a blue shifted neon-2 emission that was pointing to a slow wind coming from the outer part of the disk. And so here really the goal was to see, is the neon-2 spatially resolved because it should be if it comes from the outer part of the disk. So this work was led by graduate student Naman Bajaj, working with me. And what we found for both sources, one object is published, the other one, the paper is in press, is that there is a slight extension in the neon 2 with respect to the PSF. This is just one of the techniques that we have used in the paper. We use many more techniques because, of course, we wanted to be sure that indeed this is spatially extended. There was also some bonus science coming out of this Cycle 1 program. In fact, we found that one of the sources, Ticha, changes significantly its spectral energy distribution by a factor of 3. And it appears by combining these JWST and Spitzer data along with a lot of optical data that JWST captured the destruction of the inner wall while we were observing. So if you want more about this, I have a slide, but this is not the main topic of the presentation, so I'll move forward. All right, then what about the younger accreting objects? So here, instead, we focused on 4 disks that are seen edge-on. And the reason we chose this configuration is twofold. First of all, you should know that NIRSpec is super sensitive, so you cannot do any T-Tauri stars that is not face-on because it's going to saturate immediately. But the more important and scientific reason is that when you have an edge-on configuration, you don't see the star and you can better map any outflowing gas from the surface of the disk. So again, here we selected 4, and 3 of them we knew that are bona fide class 2 objects, so they have dispersed their envelope. We also chose the sources so that they had some ALMA observations from which we could infer the mass of the central star, okay? So we cannot directly observe the star, but through the gas that is detected by ALMA, you can get dynamical masses for the star. All right, so first I want to show you the spectra. So these, again, in each pixel, you can extract a spectrum, but when you combine all of them, you can get the total spectrum from these sources. And I want to show it to you. So here are the 4 sources, because this is a very rich data set. So you can see here all these emission lines. There are dozens of molecular hydrogen lines. Here I'm indicating just a few. There are dozens of ionized iron lines and other ionized species in this spectrum. And also I would say beautiful CO fundamental emissions. So you can see here the R branch and the P branch detected in all of these sources. In addition to emission lines, there are also absorption features from ices. You can see here water ice, CO2 ice, CO ice. So while we have not presented the analysis of all these different species in this paper, there is still a lot of work to do to characterize both the winds, but also, I would say, the ices that are present in the midplane of this disk. This is really, again, a very nice data set. But again, the focus of today's talk is on the winds. So now I want to show you the spectral imaging that we produced from this data set. But before showing them, I also want to say that for me, generating those type of images was really, and seeing them was really a wow moment, because I worked for a decade again on these high resolution spectra, imagining how these winds would look like. And finally, I could see them. So this is, I think, a beautiful image from one of the objects. Again, this is an edge-on disk. This is a composite of these 4 panels that I'm going to describe to you. We don't see the star, so I place a fake star there. This is the disk midplane. And then what you see here on the right side are spectral images in different wavelengths. First of all, down here, you have the continuum emission next to the molecular hydrogen line. And you can see that this is tracing essentially the surface of the disk. This is scattered light from dust. On the top, we see how the iron 2 emission looks like. So you can see that it's very different from the surface of the disk. It's collimated, so it's very narrow. It's extended. This is 1 arcsecond. The distance of Taurus is 140 parsec, 40 AU, sorry. And even it's not shown here in the paper, we describe that although NIRSpec doesn't have high spectral resolution, this is a fast flow because we can see, in spite of the configuration and in spite of the NIRSpec low spectral resolution, we can see that this side is blue shifted with respect to the bottom one. So this is the part that comes towards us. But what is really novel here are the images on the right side. So these are these cones that are different from the disk surface, are these winds that we were searching for. And while there are a few observations from the ground in H2 in molecular hydrogen, these are much superior quality. You can see much better the shape of the winds. You can see better that there is a kind of lack of emission in the center. And for the first time, we can also see this cone-like morphology in the fundamental CO. So here, this map was generated by putting together all these different row vibrational lines that you have seen in the previous one, spexel by spexel. All right, so this is one object. We have 4 of them, and we see the same morphology. So we always see that the iron 2, which is this collimated jet, is encased inside the H2 molecular hydrogen. And in the case of HH30, where we also detect the CO, we see that the CO is outside, essentially, the H2 molecular hydrogen. Thanks. Yes.
Sorry, 2 questions. I
No,
came in for 2. But you had a quick question with the CO. When you put all the P and Q branches all together, did you try to separate any of those by like energy of those levels to like see if there was any difference in the width of the cone?
I tried, but I didn't have enough sensitivity even for this object. But yeah, definitely, this is something that should be done. Yeah, Caitlin?
Do you have another question?
Nope.
Do you understand the asymmetries? It seems like there's a...
Yes, absolutely. Yeah, no, this is a great question. And in the paper, actually, we said that, okay, so there are 4 objects. 2 are asymmetric, this one, and 2 are symmetric, okay? And we said in the paper initially that the asymmetry is also an evidence for MHD winds, because MHD winds, because if you look at the simulations, right, if you have anti-parallel magnetic field with respect to the spin of the disk, you can generate these asymmetries. The referee didn't want that. And so it's not in the paper, but we re-stressed this in the follow-up paper where we could measure, which is not a Nature Astronomy paper, but it's an important paper, where we could measure the, so the problem was extinction. At that time, we didn't have extinction, and the referee argued that this part could be much more extincted than the upper part, and therefore we cannot claim that. But then we measured the extinction using the iron lines in the jet in a follow-up paper that I will show you later, and they are similar, and therefore extinction is not the cause, okay?
Can I skip? Sorry.
Yeah.
HH30 is like the famous HST jet image.
Yeah.
People and like maybe some of the younger people in the audience don't have that image like in their head, but it's like.
Yes. The jet is amazing. It actually, I think actually.
Do you have that image here?
I don't. Yeah, so the focus here is really on close to the star. But yeah, the HST is amazing because it's very long. Yeah.
That's also very close to HH tau, and you know, the beautiful image is right in the, like a neighbor of that. And I have a question about the so
go ahead.
So one question is, so I think that, is there any other H2 transition that was strong enough?
There are tons of H2 transition, and I will show you beautiful work
so that actually the trace a different temperature.
Yes,
And-
and no. So we looked at the opening angles,
Yeah.
actually even for this paper, but there isn't much of a difference.
Oh, so within the upper one, lower one, you see the different angle,
Yeah,
Yeah.
here and here, yes.
right.
Yeah, there is distinct.
but not between the other
The H2
transitions.
lines, no. So one thing we did in the paper, again, using this high resolution imaging, is to measure the opening angle of the jet, the opening angle of the wind. So here you can see the traces of the jet, the traces of the wind for the different objects. And more importantly, we could measure also the intersection of the wind towards the disk midplane, and found that this is in the planet-forming region, so inside 7 astronomical units. It's the first time that we go so close. For AGE-30, which Caitlin mentioned as a beautiful jet, but also as a beautiful wind from ALMA, we did this composite image in the paper. So here in green and blue is JWST data, and in red now is the ALMA CO 2-to-1 transition. And you can see that this nested morphology that we saw with JWST extends in the millimeter with ALMA. These are the traces only for JWST, just to stress again the point that the CO rho vibrational is actually outside the H2, so the location where it intersects the outer part.
Just one more.
Yeah, go ahead.
Is it shocking? Is it surprising that it's optically thin enough to see this like it's a slice?
This one?
I'm just, yeah, I mean, if it, right.
It's optically thin. Yeah,
Obviously it is, but
it
like,
is
that's not surprising.
I don't know. I mean, to me, when I saw the images, everything looked interesting, but surprising not too much. I would say we were expecting H2 to be thin. So I think it's the main conclusion of the paper. I want to stress that it's not just the nested morphology, but it's the nested morphology together with the midplane intersection and together with this vertical and radial extent of the wind that really tells us for the first time that what we are looking at is an MHD, radial extended MHD disk winds that can drive accretion. Now, we have 4 objects, that's not much. So I think more sources are needed here, and we have an approved Cycle 4 medium-sized program to extend this type of data, and Sophie Clark here is a graduate student at the LPL, and she will be leading this analysis. Here is the paper that is interesting in relation to Caitlin's question. So this is led by Naman, and this is already published. And so here we were looking at all these different emission lines and creating maps for these emission lines at the shorter wavelengths of NIRSpec. So here there is also an estimate of the extinction. I don't have that figure, but you can see it in the paper, because what is relevant for this presentation is the estimate of the mass accretion rate. So these are edge-on sources, therefore you cannot directly measure the accretion rate onto the star. You need to rely on the jet, but there are many transitions that trace the jet, so you can constrain the jet mass loss rate and therefore infer the mass accretion rate. So these are typical accretion rates given the masses of these objects. So I encourage all of you to look at this paper led by Naman for many interesting results. All right, another thing that is happening with this data set, which is led by our collaborator Tracy Beck, is to measure now the H2 mass loss rate, the mass that we can detect with NIRSpec. So first of all, you need to know what is the temperature of that gas. And so what you see here is a temperature map for HH30, the same object. How do you get the temperature? Well, I don't know who asked this question, how many lines we have. So there are many H2 lines that you can use spexel by spexel. So this is just one of the spexel here. And each of these points is an emission line from H2 from our spectrum. And so from the slope of this rotational diagram, you can infer what is the temperature. So here for the first time, we have a temperature of a wind. And you can see that the temperature is pretty high. And then because the emission is optically thin, you can use the knowledge on the temperature, the luminosity in the line. And for each of these H2 transition, you can measure the mass flow as a distance from the star. So now you can look here at the value. This is 10 to the minus 10 solar masses per year, so it's low, but we should not be concluding that this wind is not driving accretion, because this is only a small portion of hot gas that we see with NIRSpec. We are working on putting together multiple tracers, looking also at MIRI and also again ALMA, and it appears as actually there is a increase in the mass loss rate as you move outward. And I want to mention here that ALMA, I think, will be key to figure out if these winds are really driving accretion. So with JWST, you can also look at how frequent are this type of flowing emissions. So we have an approved finest project where we are looking at over 60 inclined disks with a range of stellar properties and mass accretion rates to again estimate how often these extended wind-like morphologies are present. We see already the more than 40 have spatially resolved outflow, and we see that asymmetries are common. So this is an example again of a wind. The wind is seen on one side and not on the other side. These are 3 different H2 lines, and this is the neon 2 that traces the jet. So just to mention, this is in, it fits with this picture that we put together based just on high resolution spectroscopy, because this is a high accretor. So the jet is seen in neon 2 and the wind is molecular. All right, so here are, I would say, the 2 main take-home messages. So if you look at the population level disk properties, you find that MHD wind-driven models seem to do a better job in reproducing the data. And if you look at the wind themselves, then we see these radially extended winds that could drive accretion. So why this is important? This is important because wind-driven accretion leads to fundamentally different dust transport, planet formation, and migration than the classic viscous disk. I don't have much time, but I want to flip through 3 cases to illustrate that. First of all, let's consider something that we know from the solar system for 2 decades. So we know that in the outer part of the disk, like in this Jupiter family comet, there are grains like carbon aluminum rich inclusions and also crystalline grains that formed in the inner part of the disk. So somehow you need to have a mechanism to transport these grains that form the 0.1 AU out to 5 AU or something. So you could do them maybe with viscous evolution, because you have angular momentum and therefore transport of material further out, but you can also do that from winds. And this is a paper showing how you can lift essentially from the disk surface of the inner disk submicron size grain. You can anneal them, so you can crystallize them, and then you can transport them further out. Second things, we all love disk substructures with ALMA. And often these substructures are connected to forming planets. Well, if you look at simulations of wind-driven accretion, like this one, here is the wind, here is the disk midplane, you can see that the density of the gas is not homogeneous. And when you don't have homogeneous density, you can create pressure traps for the dust, and you can actually generate also these substructures, in some cases similar to what is observed. So this could be another way to get the substructures without a planet. And then finally, I want to mention that the evolution of the gas surface density is different in viscous disk with respect to MHD wind-driven disks. So the viscous disk is here in blue for 3 different times, and you can see that the evolution of the surface density is smooth, so the disk is depleted smoothly. However, in a wind-driven accretion disk, you see these gray lines and red lines, they are sometimes not smooth. And then it means that if a planetary core is forming, it's not essentially, it could invert its migration because the gradient of the pressure gradient in the disk is not pushing the planet always closer in. And so there are in fact simulations, this is a semi-major axis function of time, showing that core of planets could move outward instead of moving inward in this wind-driven accretion disk. So that's where I want to end, again, with the take-home messages. And I want to say that these observations, I think, are really exciting, and they could maybe change the way we think about disk evolution. And so I hope that all of you will consider this new paradigm. And if you are an observer, perhaps consider how your data could be interpreted differently in this new paradigm of disk evolution. And if you are a theorist, maybe consider how your theoretical models are going to be impacted by wind-driven accretion. Thank you.
Oh, my bad. Sorry, for the emission maps for CO, did you also isolate the ice feature? Were you able
Not
to...
yet.
Okay.
Not yet. So, I mean, first of all, and Dinshan is going to work on that, we would like to measure the, be able to reproduce the total spectrum. But yes, you are right. It would be very interesting to look also how things change, especially I think for this disk. I'm really excited about this disk here because this one and that one, but this one, you see that the disk midplane is very puffed up. And so there is a lot of line of sight where you can extract your ices. Yeah. Yeah.
Thank you, and great talk.
Yeah.
Yeah, so I have a lot of questions. So question number one, can you get any polarization data to get magnetic field direction?
So I have not done that work, but you are probably familiar with, or maybe you have seen it, the paper by Richard Teague. He has used ALMA, CN transition, multiple CN transition, to estimate the magnetic field for TWhydra. So I don't know, I should check the paper. I don't know if this type of configuration actually is good for the magnetic field, but yeah, it would be very interesting to get measurements of the magnetic field. I cannot get that from
No, I know,
JWST.
I'm saying,
You would need,
you
would need another instrument.
Then my second question is about like how, right, now that we're getting into talking about like controls and transport, it really sounds a lot like X-Wing models. Yeah,
so thank you for the question. So we spent quite a bit of time in the paper to discuss that option as well. So the X-Wind is, so for those who are not familiar with it, it's a wind that is really launched from the inner part of the disk, right? And then it opens up, right? Mm-hmm. And so in the case of a class 1 or a 0 source where you still have envelope material, you could get entrained some of that material in the outer part of the disk, some of that molecular gas, and then make it appear as a molecular wind. But that's why there was on the top here these 3 sources have dispersed their nidal envelope. So this is not the case. right?
So the argument is that the X wind can't thread the disk far enough out to produce molecular outflows.
In these cases,
Yes,
because they have
because
dispersed,
it has to be coming directly from the disk at those large radii where it's cold.
Yeah, and you also see that the intersections, right? The intersections here are at 7 AU or something. So we are not talking about.
And then the classic disk wind is like what, an AU, or is it less than?
No, it's 0.1.
It's 0.1. Okay, it's even smaller because I guess it's near the truncation radius.
The truncation radius.
Okay.
Yeah.
Okay.
Joan, Joan, would you like to speak up?
Oh yeah, thank you. So related to that, I wondered whether you mentioned annealing with regard to the grains, and the annealing requires a grain being at a temperature of I don't know how much for a length of time to get the annealing process to work. That the time available is related to the velocity of the wind. So having a slower disk wind, I would think that's helpful in extending the timescale for annealing. Does it work out in any detail? Because perhaps the X wind is too fast. I forgot the details, but just wondered if you'd considered that.
Yeah, I mean, we have not measured yet the velocity of these winds, right? I mean, we can only do it indirectly once we model all these line feature, which is something that Uma and Sophie are essentially leading. But yeah, I think you are right. It would be important to measure the wind velocity and then connect it to this work as well to see the amount of time that could be, that these grains could be exposed.
Thanks.
Yeah.
Going back to these two models, the turbulent, the classic, and the new one, just for context, because I'm not very familiar with this, but what is the fraction that you would say that the fraction of the community that is moving from that classical model? And my question is because if there is still a big fraction of that community that is still using that model, what are they doing to tune the model to recover the observation? I think that's the other part.
Yeah, so, okay, so I would say that as of a few years ago, the planet formation communities was focusing on this classic paradigm, and this is I would say simply because the simple alpha disk model is easier to implement than this type of models. But recently, Tabon in 2022 developed also a simpler prescription of how a disk would evolve in this wind-driven accretion scenario. And I noticed that now several of the people working on planet formation are adopting this, and they are exploring, how planet formation looks in this other type of disks. Yeah.
Is there a prospect on correlating disk lifetimes with magnetic fields in star-forming regions?
Lifetime magnetic field.
And would you expect?
You mean? I
Yeah.
see what you mean. That a stronger magnetic field could maybe lead to a faster evolution.
Stronger localized fields.
Yeah, I don't know. At some point, I was talking with Yancy to see if we could use some of these larger field, magnetic field maps to learn something about the close environment where. But my impression is that. You would really need to do many of these measurements at the local level to see how much of the magnetic field is really threading through the disk. The other ones are more, average fields. Because in each star-forming region, you can see that also there is a large diversity of properties and dispersal. So it looks like it's more at the disk level that things are different than at the star formation level.
Do you have a question, anybody? Online? I guess Jones, the raised up is from the previous question.
Oh, yeah, sorry.
Okay, so then,
Thank you.
thank you, Ilaria. Let's thank speaker again.
Thank you.
We'll see you next week. And Ilaria's office is